Plucking Island Site 4 highlights erosion by plucking. This island setting is typical. The island axis is orientated north-south parallel to rock structure. Flow from north-northeast cuts across rock structure. Photogrammetry reveals erosions and topographic detail. Flow lines define a 10-meter high dome. Crescentic forms indicate the north-northeast flow direction. Surfaces indicate meter-scale rock removal or plucking. Plucking occurs on upflow, on ridge, and on lee sides. Many plucking edges have been smoothed or modified. A closer view reveals plucking associated with joints. Plucking is interrelated with newest form erosion. East-west joints correspond to faults along Envy Inlet Site 2 and Key River Site 3. Surveying a 20-meter-long rock drumlin. A seashell van indicates flow direction. Note east-west orientation of regular straight joints. Note plucking and fracture sets with conchoidal shapes separate from straight joints. First, straight joints are normal to flow direction. Then, crescentic joints correspond to a free downflow phase and conchoidal plucking. Conchoidal fracturings occurs in hard, competent isotropic rock, a phenomenon known to rheologists and to our prehistoric ancestors. In flint napping, conchoidal breaks are controlled only by applied stress, not by preferred rock orientation.
Even though it has amazing integrity, and it's failing within areas where they're not completely exploiting the natural joints.
Yeah.
It's only doing that in part. It's doing a lot of extra work here to take these blocks away.
It's incredible. Conchoidal fractures. And then we've got them down here and down here and down here and down here, so that you can just see how one slab will break, another slab will break, another slab will break.
All the way down.
Kind of vertical cracks that will just take away can you imagine this crack here? It's just going to take away that little slab.
Yeah.
But it somehow sends a shock back through the rock. The integrity is starting to lose itself here in these, and this is maybe the best example right here of the similarity of this pluck surface to these.
Well, you can see how that plucking there is guided.
Yeah.
So you can take the next thing that'll happen is you just take.
And
that
if the
slice.
flow continued, it would keep moving headward.
Mm-hmm.
So that's I mean, this rock is very hard, it has a lot of internal strength and integrity, yet the forces here are compromising its integrity by fracturing it in places that this is the natural fracture here.
Maybe they're actually formed by stress in the water.
What comes to my mind is that the force of plucking this out, whatever the agent is somehow sending a shock back through here. It's resisting being torn apart. It's torn apart, and this whole rock is under tension. Now you have these tension fractures. I don't know if that speaks to ice or water, but I think more the water argument is more the context of what we're seeing here. The juxtaposition of plucking and highly sculpted rocks that are hard to explain by abrasion from ice alone.
We keep in mind two processes. Moving ice plucks bedrock by shear stress. Subglacial flood can modify deeply the plucked break. At break, reverse flow is induced. Hydraulic plucking appears to be plausible. In our assessment, some propose that rapid hydraulic pulsing induced crescentic fractures and conchoidal plucking. We also consider that when lifted ice regrounds, the bedrock experiences intense loading and shear stress. To summarize, during the flood event, turbulent water eroded S-forms, including late-stage cavitation features on bedrock. The juxtaposition of S-forms and plucking indicates that both features formed at the same time. This involved water corrosion, ice loading, and potential hydraulic plucking. After the flood, the lifted ice regrounds to the bedrock, then start ice abrasion, polishing and striation, along with plucking by shearing stress and ice freeze-on. Here is science dilemma: how to reconstruct plucking processes. Occasionally, S-forms are dislocated in situ. Here a rock drumlin meters long is dislocated in situ. Surprisingly, ice regrounding had no major impact on the adjacent bedrock. S-forms maintained pristine form, sharp edges, with little if any ice abrasion. Next, let's look closer at modified plucking.
So what you would see is that, and put dye in it, it would come across and it would turn back and start rotating in there. And where it's rotating, in that whole area, is at really low pressure. So it's low pressure there and really high pressure here. So the water will flow back and then it goes up and comes down again and it just goes round and round and round. And it's because of that, it's creating low pressure, high pressure, low pressure, high pressure. So it's going chung 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 chung, and eventually it cracks.
Mm-hmm. And you can see here there's some stress.
You've got a stress crack right there.
Yeah.
And you can see just teeny ones there which are associated with this face. Little depressions or pits, maybe 3 millimeters across, a whole pile of them, and that's because of cavitation, and the cavitation's occurring down from this step. So we've got a combination of cavitation here, fractures here, and taking off blocks away from here. And the same here, we would just be taking blocks away, and there would be fractures through there. Wow.
One hypothesis to consider is that crescentic fractures result from hydraulic pulsing on the downflow side of a river's eddy at a topographic step. arcing of crescentic joints indicates that a force propagates opposite to flow direction due to a pulsating pressure field or to ice load impact.
Down there so quickly, I don't think it can. The only thing that can happen is the flow comes over towards you, and in behind the wall there's a very strong low pressure, so the flow goes back again. So this thing here might actually be formed by a flow going that way.
Mhm.